Hello friends, welcome to the session on oscillators. In this session, we'll be discussing about advantages of negative feedback. We will see what we mean by negative feedback, and we will see what are the different advantages that you will get when we use the negative feedback with amplifier circuit. Friends, you know that you are viewing this session on my YouTube channel Learn with Prakash Kanade, and do subscribe to the channel to see many more videos on the subjects of electronics and computer science. So we know that whenever we have been given an amplifier, when the output of the amplifier is coupled back to the input of the amplifier, then that is being called as a feedback. When the feedback voltage is 180-degree out of phase with the input voltage, then this feedback is being called as a negative feedback or degenerative feedback. As shown in this diagram, suppose we have been given an amplifier A and the output VO dash is coupled to the feedback network having the gain beta, then the feedback voltage will be beta times VO dash, and this voltage will be coupled to the input. And when this voltage is out of phase with the input voltage, then that is being called as a negative feedback. Negative feedback is actually of no use as far as oscillators are concerned, but with amplifiers, you will get several advantages of using negative feedback. Say for example, we will achieve the gain stability, we will have the increased bandwidth, there will be very much less distortion, the noise in the circuit will get reduced, the fidelity of the circuit will get enhanced, and we can adjust the input and output impedances as per the desiredness of the circuit. So friends, some of these advantages such as gain stability, increased bandwidth, less distortion, and reduced noise will be discussed in detail in this session. So let us go for the discussion of the gain stability. So in this session, we will see how the amplifier gain is stabilized whenever we make the use of the negative feedback. Now we know that the amplifier gain with the negative feedback is being given by the expression A dash is equal to A divided by 1 plus A beta, where A is the open loop gain of the amplifier and A dash is the gain of the amplifier with negative feedback, and beta is the feedback ratio. So one can easily observe that the denominator term is positive, and therefore the gain of the amplifier with negative feedback is reduced. Now when we take the logarithm to the base e of both the sides, then we can write the term log of A dash is equal to log of A minus log of 1 plus A beta. Now we will differentiate both the sides of the equation, and when we differentiate both the sides of the equation, we can rewrite the equation as dA dash upon A dash is equal to dA upon A minus beta times dA divided by 1 plus A beta. So this is just nothing but dA in the bracket 1 upon A minus beta times 1 plus A beta. Now when we make the denominator common, A into 1 plus A beta, then in the numerator we will get 1 plus A beta minus A beta will get cancelled out, and therefore we will get 1 divided by 1 plus A beta into dA upon A. Now in this equation, if the factor A into beta is much greater than 1, then we can rewrite this equation as dA dash upon A dash is equal to 1 upon A beta into dA upon A. Now you can easily observe that the change in the gain is being stabilized because the change in the gain is being divided by the term A beta. Say for example, suppose the gain of the amplifier is 400 and the beta, that is the feedback ratio, is 0.1, and suppose the gain of the amplifier is varied or is reduced by 20%. Then we can easily say that dA upon A will be 20%, that is 0.2. Now the change in the closed loop gain, that is dA dash upon A dash, which is equal to 1 upon A beta into dA upon A, and this is just nothing but 1 divided by 400 into 0.1 into 20%. So this is just nothing but 0.5%. It means that when the amplifier gain is changed by 20%, then the gain of the amplifier with feedback is reduced by only 0.5%. It means that the gain is 40 times less changed whenever we make the use of the negative feedback. So this confirms that whenever we use negative feedback with the amplifier, then there is much higher gain stability. Another advantage that we get with the negative feedback is the increased bandwidth. Now bandwidth, we know that it is determined by using the frequency response of the amplifier. Now suppose we plot the frequency on the x-axis and the gain of the amplifier on the y-axis. Then the bandwidth of the amplifier without feedback is actually equal to the difference between the lower cutoff frequency f1 and higher cutoff frequency f2. So whatever is the highest gain of the amplifier, we multiply that gain by 0.707, and so that we will get the two frequencies. The first one is called as the f1, which is the lower cutoff frequency, and f2 is the higher cutoff frequency. Therefore, the bandwidth of the amplifier is being given by the formula bandwidth is equal to f2 minus f1, where f2 is the higher cutoff frequency of the amplifier and f1 is the lower cutoff frequency of the amplifier. Now we know that the gain bandwidth product for any amplifier can be given as A into bandwidth. So this symbol here implies the multiplication symbol. Now because of the negative feedback, suppose we have used negative feedback with the amplifier, then we know that the gain of the amplifier will get reduced because of the negative feedback. But we know that for any amplifier, the gain bandwidth product has to remain same in both the cases. And therefore, if gain is reduced, then it is natural that the bandwidth of the amplifier will get enhanced. Therefore, we will have the new lower cutoff frequency and new higher cutoff frequency. The new lower cutoff frequency will be f1 dash, and it can be given as f1 divided by 1 plus a beta. That is, you will observe that the f1 dash is being decreased. And the new higher cutoff frequency will be f2 dash, and this f2 dash can be given as f2 into 1 plus a beta. That is, f2 dash is increased. So as shown in this diagram, suppose this is the original frequency response curve of the amplifier. This is the original f1, this is the original f2. Now, because of the feedback, f1 is decreased and it becomes f1 dash, f2 is increased and it becomes f2 dash. So because of the negative feedback, you can easily observe that the bandwidth of the amplifier is enhanced. And therefore, it will confirm that the bandwidth of the amplifier will get enhanced because of the negative feedback. It means that the amplifier now can handle a larger range of frequencies when the bandwidth is increased. Whenever we make the use of the negative feedback with the amplifier, then the amplifier will have less distortions. Suppose we have an amplifier, and suppose there is some distortion voltage D, and because of the negative feedback, this distortion voltage is changed to D dash. Now we can say that D dash is just nothing but X into D. So this symbol will specify X, and it is not a multiplication symbol. Now the fraction of this distortion voltage, that is B D dash, will be fed back to the input of the amplifier in the negative feedback. And therefore it can be written as B D dash is equal to BXD. After amplification, this voltage will become BXDA, and this voltage is antiphase or out of phase with D, that is the original distortion voltage. And therefore the new distortion voltage will be D dash, and it can be given as D minus BXDA. So one can say that D dash is just nothing but XD, and D dash is just nothing but D minus BXDA. Therefore XD is equal to D minus BXDA. And therefore we can rewrite the equation XD in the bracket 1 plus beta is equal to D, or we can write X is equal to 1 divided by 1 plus A beta. That is, the new distortion voltage because of the negative feedback can be given as D dash is equal to D divided by 1 plus A beta. And one can easily observe that this distortion voltage is less than the original distortion voltage D. And therefore we can say that the distortion voltage in the amplifier will get reduced or will get decreased because of the use of the negative feedback with the amplifier. It is also possible that the noise in the circuit can also be decreased because of the use of the negative feedback. Suppose we have been given an amplifier, and suppose the signal is being applied to the amplifier, and suppose some noise is also getting added into the signal. Then in that case, the output of the amplifier can be given as XOT is equal to XST into A1 plus X noise T into A1. And therefore, in such a case, the signal to noise ratio SNR can be written as XX square divided by X noise square. So noise is an unwanted signal and it may get added into the input signal. Now the signal to noise ratio, if you want to improve the SNR signal to noise ratio, then it can be done by using negative feedback. Now suppose this is a original signal XX, it is being a clean signal, it is amplified before it is applied to the amplifier. Suppose this is another amplifier A2, and then this signal is being added with the noise and it is applied to the another amplifier A1. And suppose some part of the output voltage through the feedback network beta is being coupled to the original input signal XS. Then from this figure, one can easily write X2T is equal to XST minus beta times X2T. X1T can be written as A2 into X2T plus X noise T. XOT means output voltage can be written as A1 into X1T. XOT can also be written as by rewriting the equation for X1T as XXT into A1A2 divided by 1 plus beta times A1A2 plus X noise T into A1 divided by 1 plus beta times A1A2. So therefore, we can write the signal to noise ratio as XX square divided by X noise square into A2 square. So one can easily observe from this equation that the signal to noise ratio is being enhanced by a factor A2 square. And therefore, whenever we want to improve this ratio, signal to noise ratio, that is whenever you want to reduce the effect of the noise on the amplifier, then the negative feedback is always useful. Thank you friends for viewing the session. Hopefully you have understood what are the advantages of using the negative feedback with the amplifier circuit. Thank you all for viewing the session.